I think maybe not take very long because I'm going to guide you on the continue with the precast connections. Wait, I have to close some of the thing. Give me some time. Okay. Before I forget, just now I have regarding the regarding these projects. You need to take a video. So the video is maximum 10 minutes. Okay, for both. Means that for precast concrete design and the pre-stressed concrete design, the duration of the video that you can go is up to maximum plus minus about 10 minutes sufficient. No need to too long. Okay, no need too long for the video. Okay, I have to find out my notes first. 4 minutes. The because it's the first semester offer and this is the first time I teach. So therefore it have maybe not so complete. A lot of things actually I have also last minute and I did not prepare well also. I try my best. Maybe just take from snap from some of the books and so on, just combine it without. Okay. Okay. Okay, let's now. Okay. So class, are you ready? If you are ready, can you please comment one? Then we are going to start now. Okay. Okay. So hopefully by before one, we can finish out. Okay. I know you are hungry. Just now I go to take some. Okay. Wait, there are so many. Okay. So now want to record, then we can do it. Okay, still before 12. So good morning, everyone. Good morning, everyone. Now we go in the precast joint. Last week we have discussed the bearing, design of the bearing based on the Euro code. And at the end, I have shown you the design, the bearing, give you some equations, some requirements. Is want to design the bearing according to the British standard. British standards, the bearing length, you name it as a width, compared to this Euro code is opposite. The length and the width is opposite way. Okay. So, but however, if you have look at the in Euro code 2, if you design the bearing, the process is longer. You have to calculate the A1, A2, A3, delta delta A2, delta A3, and then only you get the bearing length, required bearing length. However, in the British standard, it has simplified it. It has really simplified it and much simple. Okay, much simple, and based on the bearing width. Okay, the load divide by the bearing width and the length. Okay, you want to get the length by limiting the allowable bearing stress only, either 0.4 FCU or 0.6 FCU. Okay, that is what we use in British standard. Okay, so now and last week I have described a little bit about the corbel, one of the connection that widely used between the for beam and the column, beam and column. Okay, and corbel, it can be divided into shallow and deep. Okay, and deep, and we have briefed to you a little bit about the theory. Okay, so today we are going to focus on the design. Design here, initially I got thing one to show you in Eurocode 2, but at the end I show you the example because of the time. Therefore, I decided to just show you the based on the British standard lah. But however, the concept are still the same. We are only in Eurocode 2 have some more requirements. Small thing you need to calculate. But in British standard, the concept we still based on straight and tight system. Okay, straight and tight system. So Bihong, you are here actually. Maybe can give you an idea. Actually, you can see how in your report you have mentioned there's a table. So actually, you may think about it, because although we say we are going to produce the design table, but sometimes from time to time, this morning I think actually if you can based on that one to derive, if based on the Eurocode, you just change the requirement of the Eurocode. Some especially the stress diagram. Actually we can develop a table. Actually, there's a figure that used in the design. Okay, so now we focus on the design of corbel based on British standard. Okay, design of corbel based on British standard, we can based on two methods. One is the strut and tie system. Okay, this one is widely used. This one widely used. Okay, another one is shear friction methods. I can say the first one is more widely used and more straightforward also. And the requirements, some of the requirements almost the same as in the standard. When we propose the dimension of the this corbel, okay, this is a H1. Okay, this is a H1. Means H1 must be greater than 1 over H. Usually, and this one is AV. Okay, this is AV, and this one is a bearing plate lah. Bearing plate, whether we have it or not, and the reinforcement usually we're going to provide like this. We're going to provide like this, and these are the link. These are the link. Okay. So now, if based on a strut and tight force system, okay, this is strut and tight force system. If you look at a connection here on the left, on the left here, okay. Based on British standards, this is a now if you apply the load like a short cantilever, because this is a short cantilever, is it? It is a short cantilever that you apply a high point load here. Okay, so this on top will be under tension. Okay, on top will be under tension. Fs is a tension force, and then at the bottom parts here will be under compression. However, the force is not vertical. It is in the diagonal to form like a triangle. Okay, so this is in diagonal here. These are in compression. This will be in compression. Then there is a angle here. So this angle. So from here we can draw out the stress and strain diagram of this connection here. Okay, of this connection. Basically, the ultimate strain of the concrete still 0.0035. Okay, still 0.0035, and the stress block is still based on an ultimate limit state. It's still as a rectangular. We can simplify as a simplified rectangular stress block. Suppose it's a parabolic. The difference here now, the FC now is not totally FC we have to multiply with the angle cos beta. If you look at here, the FC is horizontal. We want to convert it horizontal. So basically, we have to multiply with a cos beta here. The compression here, we have to multiply with a cos beta here. Okay, so mathematics. So, and the stress, the maximum stress 0.45 FCU. Still remember just now in the precast, the horizontal shear stress, we are under compression. We assume the whole and okay the what the precast slab, composite slab on top, we assume all the topping cast in situ all are in compression, so we can calculate the force, the compression force, is it, which is 0.45 FCU multiplied by the effective wave multiplied by the depth here. Okay, here 0.45 FCU. Okay, 0.45 FCU basically this is the value maximum stress. So maximum stress, okay, this 0.45 FCU cos beta here. This is under stress. This is under stress. We are in the unique stress rather than the force. Okay, in this case, this is the stress. So the stress we have to multiply by a cos beta as a cos beta. So from here, actually, based on this system here, based on the stress block diagram here, actually we can derive the equation. We can derive the equation. So you have to refer to a step that I just take from the handbook. I just took from the handbooks. Okay, handbooks. You refer to the appendix. Refer to the appendix here. Based on this one, based on this one, okay, based on this stress strain curve here, especially the stress block diagram here, we can actually derive the equation. We can derive the equation here. Okay, but before this, these are the shear, these are the step, the design step. These are the design step. We list it out. Okay, this the first one actually you can based on the shear actually how to get even to get the suitable depth. Or depth. Then when you get the depth, actually we can multiply. We can get the overall dimensions. So remember here, the shear, because it is very near to the support, the shear strength can be enhanced by, or the shear strength or the shear stress. Okay, we can enhance the resistance. The resistance can be enhanced by 2D over AV. Remember, this is can be enhanced by 2D over AV. But in this case, actually, this one is the depth. How to get the depth? You look at here, why you got 2D over AV here. Actually, it's enhancement because of the dimension is very, the dimension is very near. V over BD. V is basically what? V is this one. Okay. BD is the dimension and the effective depth B. Okay. So this is a stress. The design stress means applied due to the external load. Then it must less than the allowable. Okay, allowable. VC basically is the concrete shear strength. Concrete shear stress here, here VC. Then we can enhance the VC. We can enhance the VC by multiply with 2D over AV. Therefore, from here we can rearrange. Actually, we can get the D We can get the D here. We can get the D here. So this is the way actually how to estimate the suitable depth to be used to get the dimension. Okay, to get the dimension. So in this case, the VC, suppose there is an equation 0.79 divided by gamma m and so on. But in this case, if eliminate in to get the dimension, you can use directly limit it to the maximum allowable shear stress, which is 0.8 FCU or 5 megapascal, whichever is smaller or whichever is lesser. Okay. Then we have a force here. Okay, Fs here. Okay, we have Fs here. So basically, the Fs, if we have a combo, Fs is T plus Fc cos beta and so on. Then the FC cos beta actually is V multiplied by AV over Z. If you look at, go back here, if you go back to the diagram here, basically the cos beta, this is vertical component, is it? Fs, we want if we bring it here, this here, then the cos will become Fs here, huh? Okay, we have Fs here. So this is how we get this component. But never mind. Okay, of this is all right. It's all right, no problem. So the compressive strut forces, just now I mentioned at the look at the rectangular stress block, the simplified rectangular stress block, 0.45 FCU, okay, multiply by what? Because you look at here now, this is the neutral axis here is X, is it? So this one in British standard, we based on 0.9x. In Eurocode, it is based on 0.8, is it? But Eurocode based on FCK. Eurocode based on FCK. But the four system we can still based on the same concept because short and tight system. These are not say the only in British standard based on like this. The rest not like that. No, this is whatever code we can base on this concept to derive the equation. It's only here if you base on Eurocode 2, the value here is different. This is 0.567 FCK, is it? Okay, it's only difference here only. Okay. But and also in Eurocode, this is 0.8x here. So from here, we can actually substitute, we can get the FC is a force. FC is after this, actually, what we don't know here is we don't know what is X. It's like in the beam design, we don't know what is X. What is X? We have the dimension already, but I don't know where is the cutting point, the X compression and tension, is it? So we have to calculate. We have to calculate. So based on the equation of both equation, actually, they are trying to derive derivation of Z over D. They want to get Z over D. So here you can look at the derivations. V equal to FC sin beta V, is it? This is a V vertical load, is it? And so on, is it? So V is FC sin beta and so on. So at the end here, we will get actually what we want. We derive at the end from the derivation here. Okay, at the end is we want to get an equation. Okay, an equation V over FCU equal to something like this in terms of AV, in terms of Z. Okay, okay, and D. So now, like Bi Hong, actually, your case actually you can base on like this. It's only different here. You can get V over what? FCK. Can base on V over FCK to get a derivation to get V over FCK. The difference here, there are some value here will be different, but at the end you'll get an equation something like this. So from this equation, actually you can substitute with different Z over D. Substitute with different Z over D with different AV over D and so on. You can actually or you can substitute with different V over FCU and so on, the value you will get, and also over AV over D with different Z over D, you can develop a design chart. Actually, this is a design chart, okay, that used for after this, you can see we're going to use this chart in the design. Okay, we can use this chart in the design. Therefore, if you are using Eurocode, actually, I think maybe in Kim Elliott books is different. In Kim Elliott, actually, the example, okay, the example is a bit different. They are not based on, doesn't have this kind of chart. So what we can do, actually, you can develop a chart. If there's even develop a chart, actually can be, is also a very, I mean, it's very good already. Very good. You can, for you to come up to form up the chart, but you need maybe some Excel and so on, because we are repeating. Once we form out the equation already, okay, we just put in different value, and then we can plot out the graph. We can plot out the graph. We can plot out the graph. Okay. So and then they have some requirements. There's some requirements and so on. Okay, so this one, the stress of the to how after this in the example you will look at it. We will look at it. You can use either directly use the equation, or we can go back we can use this equation. Okay, so in Eurocode 2, Fs also the deflection, the equation also a bit different, is it? Because of the S is 0.8x. S is 0.8x. So therefore it come out a bit difference here. The value a bit difference here. Okay. So these are the and then after this, these are the detailing. I can say these are the detailing, anchorage and detailing that we can provide. But in reality, actually sometimes I can say most of the time we use this one. Okay, I can say we are not going to welding and so on. We use this one. If that's say sufficient, we can just direct bend it and so on. And the horizontal link is minimum. The minimum still we based on, okay, after we have get this after we have get the Fs, I mean after we have get the T here, to get the reinforcement is just divide by the stress. Okay, just divide by the stress. So either the stress, the steel is U or not. That's all. Okay, whether it's steel. If they say the steel is U greater than the U strain, then we use the maximum strength of the steel. If not U, we have the proportion based on the equation here, based on this equation here, based on this equation. You must actually good. I mean, it's all these are related to what you will learn in your RC design, related to your RC design here. Okay, or you can actually proportion here, or we can just get the strain and then we can proportion to get the stress here. Okay. After this, the minimum of the reinforcement here is, it's not mistaken, is 0.5 0.5 minimum reinforcement. In the example, yes, given in the example, given in the example. And the link is usually we are going to provide in 2D, 2/3 of the D, the link. Okay, 2/3 of the link. So all this is in the example. Okay, today for precast concrete design, what we are going to focus here, the corbel and the nips only. Okay, corbel and the nips. Hopefully by before 1 we can finish up, because some of it I just now I already show you all just now at the beginning of the this morning, the beam that I have missed out, that one I will cover it. Okay, so these these are the main reinforcement. Okay, these are main, but in actual way sometimes we like this. This one bend it out, come here, we are going to bend to here. Okay, we can bend to here, either we want or we don't want, but usually sometimes we got just extend a little bit only go in to here, in a loop here, in a loop. Okay, actually you look at this one, but we are always actually in the loop here, in the loop. Okay, okay, so now we look at the example. Okay, example. In the example, the design. Okay, okay. Before go to the example, still under British standards here. Okay, it's only actually repeating again, repeating some of the thing. If we take out in the clause in the British standard, in British standard it is stated in clause or section 5.2.7.1. Okay, there's some give you some idea of the dimension here. Okay, the idea of the dimension. The distance AV between the line of the reactions, okay, to the supported load, the line of the reaction actually is from the face here, inner face here, okay, outer face here, sorry, consider inner or outer face, okay, from here, is less than D, okay, it's less than D. So this one, the AV will less than D, AV will less than D. If greater than D, what happened? Actually, if greater than D, is not going to have something like a struck and tight model already. It's something like a short cantilever beam already. You have to just go and get the AV multiplied by what already? Multiply V multiplied by AB already, like some sort like nips that we are going to look at it, just a short cantilever. Okay, short cantilever slab or short cantilever beam. Okay. And the depth at the outer edge here of the contact area of the supported load is not less than 1/2 of the depth of the at the root of the corbel. Basically, this one, the dB here is not less than h/2 something like this. Okay. They give you some information. Okay. We can base on the strut and tight system. Just now I look at it already. The strut and tight. The corbel should be designed at the ULS, ultimate limit state. Okay, using the appropriate partial safety factor on the reinforcement and concrete. Okay, so means that material gamma m of the material we have to use So this is like similar to normal reinforced concrete Okay, but the magnitude of the resistance provided to horizontal force, which is the T, should be not less than 1/2 of the design vertical load of the corbel. So what it means here actually? So you based on here, this T force, the T here that you're going to design, you're going to get it, that the horizontal force on top here, which is the tension that you get, must not less than half of this V vertical load. And then, for example, let's say the V is 1,000. The T that if let's say you get it only 300, so you have to use 1,000, half of it, 1,000 divided by 2, which is 500 to design for the T. Okay, for the T, not less than 1/2 of the depth. No, this one of the force. This one, 1/2 of the design vertical load on the corbel. Compatibility of strains between the strut and tight at the corbel root should be ensured. So that one we'll look at it already. The stress strain curve the stress strain curve that we're going to use. Okay, something like this. Okay, this is similar to just now. Okay, similar to just now. The same thing. Okay, why 0.405? Because it's 0.45 FCU multiplied by 0.9. 0.9. So we'll get 0.405. Okay, this one B. Okay, Bx cos beta. So basically the force, compression force, is where Fc equal to 0.405 FCU Bx cos beta Okay, so strain, ultimate strain of the concrete here, compression 0.0035. Okay, so we can get the strain of the steel at this level, is at this level okay, at this level. This is S this is S. Okay, same thing this one is V, this is AV. Okay, and what as a strut and tight, the depth of the corbel at the face of the support must be sufficient. That's why the depth we must provide sufficient to eliminate the possibility of the shear failure. Okay, we are going to avoid that one. Okay, the design shear stress, maximum design shear stress, we must make sure that V over BD, just now already mentioned, must less than 0.8 SCU or 5 megapascal, whichever is smaller. Okay, so can be enhanced. Already mentioned, the concrete shear strength can be enhanced by a factor 2D over AV because the point load is very near to the support. The point load is very near to the support. Okay, the size of the bearing plate transmitting the ultimate design load VU to the corbel should be calculated using a bearing stress not greater than 0.8 FCU Okay, maximum is 0.8 FCU. This is the bearing stress that be allowable up to it. Okay, corbel design side, we'll look at it just now. Okay, we have more we can have more. Okay, so we are going to use we're going to use this chart to design in our design. Okay, shearing. Okay, theoretically, when VC is greater than V, okay, if theoretically, if let's say the concrete shear strength is greater than the design shear, so shear reinforcement is not required. But however, actually sometimes the most of the designer agree to increase the D so that V does not exceed VC. Okay, V does not. This is in the designer, they agree with this, but we are, you see, we are not going to do that. Means we are going to use this design for the link. Okay, the shearing is what we need to provide. The shearing is half of the AS required. AS is the tension, based on the tension on top. We are going to provide half of it. Okay, the shearing. And the link we're going to provide at the location of 2D over 3. Okay, 2/3 of the depth on top from top. Okay, because tension is from top. Okay, so these are a little bit about the theory of corbel. Corbel based on strike and type. Okay, strike and type. So now we refer to the example corbel design. Okay, we have a corbel, design a corbel for 300 mm wide column. Means the column is go that way. This is a column. Okay, this is a column. That's it. Wide is this one. The wide 300 mm. So the corbel is going to, in this case, the corbel is going to do full of the column projected out from the column. So the width here is basically is what is the 300 mm. Yeah. Okay. And to support a vertical ultimate design load of 500 kilonewton with the line of action of the load 200 mm from the face of the column. Means it's from here from here. This is 200 mm. Okay, I did not prepare my own example, but I just use it only. It's something like this. Maybe you can use maybe opposite, because I did not stop the sharing. Something like this. So this one is 200 mm. This is 200 mm. Okay. So FCU, 28-day cube strength 30 megapascal, and the steel we use 460. Maximum bearing stress. Okay, maximum bearing stress, just now I mentioned already, not greater than 0.8 FCU, is it? So it's 24, 0.8 times the FCU, 24. Assuming effective length of bearing. Okay, this is assume is 250 lah. The length is 250. Actually, you can calculate after this. Okay, so the minimum width. Okay, assumes the bearing plate, the length is 250. Okay, 250. So the allowable stress is 24. Is it 24? So the load is 500 kilonewton. So it means that the width of the bearing, how much we need to provide, basically the is 85 lah. 83.3, we get 83.3 required. So basically we have round off to 5 mm nearer, is it? 5 mm nearer. So we use 85. So this is the bearing plate we are going to use. 85 times 250. 85 times 250. Okay. Okay. This one is to get the, let's see, to get the size. If let's say there's a question come out, most of the time the dimension really given. Okay, dimension really given. You no need to calculate all this. You need to calculate all this. It's just direct use the dimension. Don't go and propose your own dimension. Just use it. Just use it. Okay. So, and the shear stress, okay, the shear stress, okay, must be not greater than 0.8 set FCU. That is the maximum allowable. So the shear stress is V over BD, is it? V over BD. So 0.8 set FCU is 4.38. 0.8 set FCU of 5 megapascal, whichever is lesser, is it? So 0.8 FCU is 30. SCU is 30. So you substitute it here, actually basically you get is 4.38 lah, 4.38. Okay, so from here basically the B we know already. B we are going to build until the whole width of the column, is it, wide of the column here. So we rearrange the equation here, okay, and we substitute this maximum 4.38, okay, 4.38. So at the end we get 380. We get 380. We get 380. Then consider this is the D, but you had to plus the rest. So in this case, you decided to use 500. Decided to use 500. If 500, so the depth here is the effective depth is 500 minus the concrete cover. It did not mention here, but in this case, you say concrete cover minus from here, from the bottom part here, the concrete cover 20 mm. Okay, assuming the main reinforcement is 20 mm also, so half of it. So the effective depth is 470. Okay, it's 470 here. So this is to get the dimension. Then you check again. If based on this dimension, V over BD. Okay, B is the width there, the wide just now. D is 470 to make sure it is less than 4.38 lah. Less than 4.38. Okay, this is the design shear stress. This is the design shear stress. Sure, you less than 4.38. We based on 4.38 to get the dimension. Then we provide bigger. So therefore, at the end, the actual design stress will be much lesser than 4.38, which is 3.55. Which is 3.55. So from here now, we draw this. Okay, this is our dimension, and usually this one here will use half of it lah. This is 500. We use half of it lah. We use half of it. Okay, we use half. Okay, and the effective depth here is from here, the reinforcement that we're going to apply up to the notch here lah. This is effective depth. And okay, so this is a strain diagram. Ultimate strain of the concrete 0.0035. Okay, so now how to get all this? Okay, and the V is 500 kilonewton. This one is what? 85 times the just now 250. Okay. So we are going to use the design chart to get the X, okay, to get the X, and to get the, after get the X, actually we can get the FT lah. We can get the FT, because why? Basically the FT based on this triangle diagram. FT is what? This is you know the angle here, is it? We know this one, is it 329? We know this is 200, is it? So we know this angle, is it? So basically based on this triangle, FT is what? FT, we can calculate. FT basically is, this is V, is it? Cos, is it? Is V cos beta here. Is it? We cos the angle here. Therefore, actually, once you get, we can calculate already. This is why how we want to get the FT. And the FT must not less than half of the 500 here, not less than 250. Okay, so now we're going to use the design chart. AV over D. Okay, we calculate AV over D. AV is the distance here, the vertical force up to the surface of the column here, 200. AV over D. D just now is based on the dimension 0.43, and the stress over FCU. Stress over FCU. Stress is V over BD, 3.55. We calculated just now. Okay, we calculated just now. Okay, so now we have these two values. Yes, these two values, 0.43 and 0.118. Okay, so what is the Z over D? We're going to get the Z over D here. Either you use this one, 0. Again, just now the value is 0.43, 0.118, 0.43. So something here, 0.43. Okay, 0.43 somewhere here. You draw a line here, and 0.118 is somewhere here. Is it? You get something is like near to about plus minus about 0.7. I can say that plus minus about 0.7 here, plus minus about 0.7 Z over D. So we get this one, you use Z over D equal to 0.7. Okay, or it may be less a bit if you draw exactly, but approximately. So Z over D we know. D is what? D is 470. Is it? D is 470. So from here, we get Z over D equal to 0.7. So Z equal to 329. Is it? Z equal to 329. So now, why you get the Z ready? Why you get the Z? Basically, you can calculate the cost. You can get the, once you get the Z, what to say? Why you get the Z? Okay, this is the Z. Okay, the lever arm here. This is the lever arm. When I get the Z here, we know the Z ready. So basically, you can get the value here, the angle here. You can get the angle here. So when you get the angle, so basically, because you can calculate the cos beta here, okay, so you can get the FT. So FT, make sure this FT is greater than what? Greater than V over 2, is it? This one is what? This is 500. This is 500. So this is 500. Must greater than this. Greater or equal. Make sure it's greater or equal. Okay, so okay, this is all right, greater. If let's say this value is less than this one, 250, 500 over 2 is 250, is it? So we have to use 250 in the design. After that, we are going to calculate the whether the steel is 460, whether the steel is going to yield or not. The steel is going to yield or not. Okay, we have to calculate the what? We have to calculate the strain of the steel. Okay, we have to calculate the strain of the steel. We know the D, we know the Z. Okay, so basically we can calculate the X, no problem with it. After we have get the, okay, after we have get the D, we know the D already, and we get the Z. Okay, so basically we can get the X. We can calculate the X. We can calculate the X. And this one, after when you get the X, actually you get dy is the distance here. So therefore, from here, we know the value here, the ultimate strain of the concrete is 0.0035. So from here, to get the strain of the steel is what? Proportion, is it? 157 divided by the X here, multiplied by 0.0035. You get the strain of the steel. You get the strain of the steel here. Where we stop? Okay, the strain of the steel. So we get 0.001755. So it's less than 0.002. How this is what? 0.002 still remember or not? I have think this one I got mentioned a few times even in the normal RC design for this is for 460 is it FY. This is, I think it's 0.87 FY is it we use. something like this. 0.002. This one, you go back and try to calculate. This is a straight strain curve of the steel reinforcement. We know that we are simplified something like this. It's only this is the maximum. Okay, U, but you have to make sure that you achieve the U strain. Okay, you achieve the U strain. So this U strain you can base on the E to calculate, is it? To base on the E to calculate. So once you get the U here, the U strain here basically is what? You will calculate out. Hold a minute, because the rubbish truck is coming. A bit noisy. Let it go first. Wait, hold a minute. Let me read some of the messages. Okay, now, so we notice that actually is the steel is not U. It is the steel is not U. So therefore, we can calculate the what is the Fs. Either you can based on this one. Okay. 700 Z over D minus 0.55 divided by 1 minus Z over D. Okay, you can base on this one because you get your Z over D already here. Your Z over D here. You get your Z over D. We have just now already calculated Z over D is 0.7, is it? You can try to calculate 0.7. Just now Z over D is 0.7, is it? 0.7 minus 0.55 multiplied by 700 divided by 1 minus 0.7. We get 350. Okay, we get 350. But remember, this equation only valid for what? This equation only valid for Fy equal to 460. Yeah, Fy equal to 460. Okay, so you get 350 lah. So or approximately it's about 350 lah. You based on that equation, or you can actually proportion it. You can proportion it. Is it? This one divided by this one multiplied by 460, I think. Okay.
So we can't see the slide.
You can't see the slide. Oh, just now nobody tell me. Oh, sorry. I did not. Sorry. Maybe you got messaged me because when I. Okay. Because when I did not I can't see your messages. Sorry. Okay. So I don't know where just now where I missed out already. So means from the strain here, we calculate the strain. We calculate the strain here. Okay, we can calculate the strain. We get it actually is not U. It's not U. Less than 0. One is 0.002. Two something. I think 0.00207 or what is it? Two something. Is when the steel is U. Then you can use a full strength 460. But if they say it's not U, means that the strain of the steel is less than 0.002, is not U. So either you can proportion, because it's triangle, is it? You can this value divided by this value multiplied by 460. You see 0.00 1755 divided by 0.002, okay, times 460 times 0.87. Don't forget, because this is 0.87. We had already substitute 0.87 on top because this one. So you how to get this value 351? Either you use this equation, okay? Either you directly use this equation, because this equation is just for Fy. This equation is for Fy equal to 460 megapascal. Okay, derive based on 460. Okay, if they say Fy equal to 500 or 250, you cannot use like this. You have to, the value is different. Or another way is something like this. Where is my okay, here. Another way is you get the strain ready. Why you get the strain here? Why you get the strain? This one, you know the U strain. This is epsilon U. Is it? Because the reinforcement is something like this. The stress strain curve is something like this. This is 0.87. This is 0.87 Fy. And this is the value of this value. This is this value. So now this value you get is somewhere here. Somewhere here. For this value here. So now you can proportion. You can actually proportion to get the stress, is it? Which is what? This value divided by this value multiplied by 0.87 Fy. Fy 460. So you get 351. Okay. So do you get it, class? This one, how to get the Fs? Can you get it or not? If you get it, can you please comment? Please comment 2. Please comment 2. Then I know you get the value. I know you get the value. Okay, good. Or I can get the value here. Not necessarily you are going to U. Okay, sometimes you're not going to U. Okay, not going to U because you not achieve the U strain. Okay, so then the reinforcement very straightforward already. Is the FT 304. Okay, FT 304. I just remove some of the thing. It's not very thing. 304. FT is 304. That's how we get it. FT divided by the stress of the steel, 351. Then we need 866 mm square. So we provide 3 numbers of 20 mm diameter. 3. We don't put like this. Either put 3T20 Put 3T20 is the provided is 20 mm is 314. Okay, 20 mm is 314 point something the each area, the cross sectional area. So 3 numbers you get 343 or 342 Okay, so which is greater than the required. We are going to put on top the endpoint, put on top here. Then minimum just like I mentioned, is it? Minimum must at least 0.5 half of this one. Okay, half of this one. Actually, once you get this one, you prove it is greater than this one, then it will be okay already. You no need actually even no need to calculate this one. No point, is it? If that say we know that the V here is less than V over 2, actually here when you apply here, you just directly here we use V over 2. We use V over 2 to calculate. Okay, but like this also can, no problem. Like this also can. Okay, minimum. Then after this, we are going to check for the shear and design for the link. We are going to check for the shear. We calculate the VC. We calculate for the VC. VC is what? VC, the equation. Okay, the VC equation. What is the VC equation? VC is 0.79 divided by gamma m is 1.25. Okay, 100 AS over BD power 1/3. Very difficult here. Multiply by 400 over D power 1/4 and FCU over 25 power 1/3. And 100 AS over BD not greater than this one, not greater than 3. If greater than 3, use 3. This one not less than 1, 400 over D. If less than 1, use 1. FCU is between 25 to 40. Greater than 40, use 40. Okay, greater than 40, use 40. Less than 25, we use 25. Less than 25, you get 1. Okay, so you substitute here. So basically, this one you get less than 1, is it? This become 1. So FCU is 30. 30 over 25 power 1/3. 100 AS over D. AS is 34943. B you have, D you have, and so on. So you substitute at the end, you get 0.59. You can try lah. You can try and calculate lah. You can try and calculate, see whether correct or not. Should be correct lah. 0.59. So how to get this 0.59? Basically, it's from this equation. VC, okay, VC. So after this, the we can enhance. This is the VC is the concrete shear strength. Okay, concrete shear strength. Concrete shear strength means concrete shear strength. So and that we can enhance it. We can enhance. Just now I mentioned to you, is it? We can enhance with 2D over AV. Okay, 2D over AV. AV over D we already calculated, is it? It's 0.43. It's somewhere, is it? 0.43. AV over D. Sorry, AV over D is 0.43. 2D over AD. So 2D over 2D over AV is basically is 1 over 0.43. Somewhere here. So where is it? Here. Okay, it's here. It's here, 0.43. So basically, the enhanced shear strength become from 0.59 become 2.73. Become 2.73. So just now got mentioned in the notes, sometimes some engineer they prefer make sure that the shear stress, this shear stress, the V, this value, where is it already just now? The value is this 3.55. The design shear stress is less than the VC. Less than VC actually is too what to say, it's too conservative. Actually, it's less than enhanced shear stress will be better. Okay, less than enhanced shear stress will be better. So they are going to increase the depth. Okay, less than this one. However, if greater than, we have to provide the link. We have to provide. We can design for the link. You can design for a link. So therefore, this is the enhanced shear strength is 2.73. Is less than the design shear stress 3.55. Just now I show you 3.55. So therefore, the link This is 246 is B minus V minus VC is what to say here. You get you confused here actually. It's something like this. This is the, I mean the spacing. I can say the spacing it can go. The spacing it can go. This one I just remove this one the thing it's not very too much. It's a lot already. Very so something like this. Okay, so B minus VC here we get a value 246 after this one we see how. So we get this one so now we are going to get the link. The link, what is the this is actually the spacing this is the spacing. Okay, from table using, we'll do this what to say this one a bit confuse you wait let me figure out. Let me figure out first just now the link, the shear link. Okay, the shear link required is half of AS required. Half of AS required. Half of AS required. I'm now not very sure. Half of AS required. So AS required how much? AS required is just now 8 something, is it? T over stress is 866. Okay, 866. So half of 866 866 divided by 2, how much? 866 divided by 2, 433, is it? 433, is it?
Yes.
Okay, 433 Okay, you have to remember this one is going to use 10 mm. You based on 10 mm, what is this? Based on 10 mm, you have to 10 mm is 78.5. You see that you need about 5 point something, is it? But you have to remember the link is going to have a loop. The link is have a loop. Something like this. This link not only provide here, it's going to turn it another side also get. So you will provide T10 here, 1 here actually is represent 2. Over the other way is going to have another 1. Okay, so the required steel here, is for if you are going to use 10 mm, is it? You are going to use 10 mm is 433 divided by, like the link is divided by 157. You use 10 mm is 2.7 or 2.8. So we use 3. So therefore the link here is how many number is numbers numbers of link is equal to 433 divided by 2 times 7 2 times 78.5 for 10 mm. This is for 10 mm. So then you get 2 point something. You get 2.8 lah. You get 2.8. Use 3 T 10. 3R or 3T lah, huh? Either you use T or R also can. You can use R or 3T here. Okay. So this is how you get three numbers here. How you get these three numbers? Okay, this one, three numbers. Now another one is the spacing. Another one is the spacing. Is it complies or not the spacing? This 3T10 need to provide what? In a distance of 2/3 of the D. 2/3 of the D. Okay, 2/3 of the D is 2/3 of the D is 313. Okay, 313 from here, from here, from here. So basically, if 313, the distance of 313 is what? Divide by 3 spacing. 1, 2, 3 spacing. 313 divided by 3, how much? 1 something, is it? The exact spacing here is only, we consider from here come here lah. Okay, it's 104 only. 104, 104, 104. So which is less than this distance 246. Okay, less than 246. So we are not going greater than 246. Therefore, everything comply lah, something like this. Okay, so what we're going to do is we are going to provide something like this. Here, this is 3 T 20, and this is 3 numbers of T10 as the link. This is our detailing. This one even is 75 mm only because after minus everything lah. Okay. Either I think we just draw like this only lah. Sometimes even the distance in actual the distance is the spacing actually is not really a big issue lah. But we provide at the upper side. We provide at the upper side. So can you get it or not, class, about the this corbel? Okay, so can you get it or not? The design of the corbel using struct and type methods, using the design table. So for Bihong, actually, is just now I mentioned to you, is actually you can look at it. Actually, to develop even a table, a design table, AV over D and the V over FCU, and just now this table, the table of AV over D and vertical V over SCU, you can actually look about it. You only have to use the criteria of Eurocode. Then this one is actually a contribution. It's a contribution. Any question, class? Before we go to the last one, NIPS is concrete. NIPS is very straightforward. Very straightforward. Okay. Okay. So the rest, how, if you can get it, so can you please comment 5? You comment 5 if we go to the last one for today. If you understand, you comment 5, then we go to the last one for today. The precast NIPS, concrete NIPS. Nobody comment. Not understand. A lot of things actually is go back to the what you have learned in the RC design lah. Okay, you look at what you have learned in RC design. It's only here, Eurocode and British standards are about the same lah. Can I continue? Okay, nobody comment. Why minimum are 343 over 2 at low bus area? Where is it? Oh, I miss the shear link. That is the requirement. That is the requirement. here in the notes got mentioned. In the note got mentioned, shearing the required is half. Shearing is half of the tension bar that we need to provide in practice. In practice, I think it's not critical. Even if that say you see, if you are the shear stress, the design shear stress is less than the enhanced shear strength. Actually, it's not required. Especially if the shear stress is less than the VC. Theoretically, we no need to provide the shearing. Okay, theoretically, we no need to provide the shearing. But it's more than that, we need to provide. Okay, within even just now B that one we no need to calculate, also no problem. Even that is what we need to do is we make sure that the shearing we provide is half of the tension bar. Okay, half of the tension bar, and then we provide at the distance 2D over AV, 2/3 over D at the upper side. Okay, near to the tension parts. Okay, so other questions or not? Okay, so the rest no respond, then we continue to the last one. Continue to the last one, which is the concrete nips. Reinforced concrete nips. Okay, just now you look at the corbel, is deep enough, is it? Deep enough, and we make sure that there's a requirement between the AV here, AV, but AV to the depth, we have to make sure it's less than the AV is less than the depth, the D, effective depth. However, now you look at the nips here. Nips here, actually the thickness is not very thick. Okay, the thickness, the nips are usually less than 300 mm deep. The thickness is not much. Okay, not greater than 300 mm Okay, it can be 200, 150, 250, something like that. So in this case, the behavior is not like corbel. The behavior is not like corbel. So what we need to do is we design as the short cantilever. Okay, short cantilever slab or short cantilever beam. So the short cantilever beam or short cantilever slab is very straightforward, is it? That one is very straightforward. Okay, so but the difference here is the AV. The AV we are taking into account here is to the inner vertical reinforcement of the wall or of the column. If the nib is projected from the reinforced concrete wall or from the reinforced concrete column. Okay, here this is the AV. If without chamfer, means that something like this, the V that we consider is to the corner outer part here. Remember here. Okay, we calculate the dimension, best dimension of the V here, we best until the end here. If we chamfer, okay, something like this, we are from here, we're taking the AV start from here. If that say there is a bearing plate, we are we assume it's from the not at the center, we assume at the outer parts here, a bit conservative. But however, actually in the design, in the actual design, sometimes if you want to make it critical, conservative, you can consider from the end here to get the moment. When it is a cantilever, short cantilever, what you're going to do is it just calculate the moment. Is it? The moment is the V vertical load multiplied by the AV. So the AV is up to the inner vertical reinforcement here. Remember here, means that you have to minus the concrete cover here and the half of the steel reinforcement here to add it. to add with a certain distance here. Okay, so get an idea or not why when we need to design as a short cantilever, or when we can design as a strut and tight system here, when the load over the D, okay, the load, I mean the shear span over the D. Okay, you refer to BS801. Actually, BS801 or Eurocode, the same thing. Eurocode also, we can enhance here. The shear resistance can enhance. Where a continuous nib is less than 300 mm deep, okay, it should normally be designed as a short cantilever slab. I already mentioned. Where just now, the load, the vertical load, I already explained just now, based on these three conditions. Okay. And the moment, we can get the moment is M is V multiplied by AB. For shear resistance, the value of VC, how to calculate VC? VC is 0.79 divided by gamma M multiplied by 100 AS over BD power 1 over 3 multiplied by 400 over D power 1 over 4 and multiplied by 5 CO divided by 25 power 1 over 3. Okay. Maybe increase, we can increase by 2D over AV. Okay, by 2D over AV. So now, last one is the example. Okay, example. I think should be more than 1 o'clock. More than 1 o'clock. Okay, look at example now. An in situ reinforced concrete nib is required to carry a series of precast pre-tension hollow core units. Okay, continuous. You can imagine, okay, continuous. It means that something like this. Like an L, maybe opposite way, okay, look at it, maybe opposite way. Okay, it's continuous, the nips here. Okay, and you need to carry the what hollow core floor units 400 mm wide times 140 mm deep, means on top of that one you carry the hollow core slab will sitting on it. Okay, the sitting on it, and the hollow core slab, the wide is 400 mm and the deep is 140 mm. Okay, precast pre-tension hollow floor units. Okay, the floor units are to span a clear distance 4.5 meter. So it's opposite the other way. The slab is the length is 4.5 meter, you can imagine, and carry a superimposed load of 5 kilonewton per meter square, including 1.5 kilonewton per meter square for scrapes and finishes. Means the load that you carry is total is 5 kilonewton per meter square. Okay, 5 meter square. Superimposed load that going to add in. Okay, the in situ concrete is to be grade C40, means FCU grade 40, and using 20 mm maximum size aggregate, and the reinforcement is to be grade 460. Okay, FY 460, and the exposure condition is mild. And this one, because this is exposure condition, is to get the some of the and the the concrete cover and so on. Okay, and concrete grade, the precast units, precast floor units can be classed as non-isolated members with a cell weight of 2.5 kilonewton per meter square and concrete grade C40 lah. Means that given to you the QK is 2.5, GK is what? GK just now have to plus okay. Sorry, the cell weight of the hollow core is 2.5. Yes, okay, something like this. Okay, from here now you see with the exposure condition and 20 mm aggregate, we shall need 20 mm cover. This is the in terms of the concrete cover lah. How to get the concrete cover? If the question come out, we will give you concrete cover everything ready lah. Okay, concrete cover is how the way to calculate the where we need to put the vertical reinforcement in the wall or in the column lah. Okay, so if we use vertical loops for the reinforcement in the nips and so on, minimum depth of the nips, minimum depth, actually they want a minimum depth is 20 plus 20 plus 8 times the bar diameter and so on. Okay, so assuming and so on. So at the end, you get actually you say you want going to use the depth is 105 mm. Okay, this is just to get the size the depth is 105 mm. Minimum we start, I can say we start it like a concrete slab with it. Minimum we'll use is 125. I can say it's better we use 125 in terms to comply the serviceability, the concrete cover, the durability lah. Okay, it is also suggested that the front edge of the nips should have a 15 times 15 chamfer. Means that there is a chamfer. Okay, and so now we look at the load. Cell weight of the floor 2.5 and 1.5 including 1.5 is this, because this is total superimposed load is 5 plus actually 1.5, but it did not mention to you is the imposed load, the live load is how much, but from here you can calculate, is it? This is 1.5 is the finishers, so 5 minus 1.5, 3.5 is the QK. 3.5 is the QK already. 3.5 is the QK. So we got the cell weight of the hollow core plus the finishing. Okay, is 4 kilonewton per meter square, and the imposed load is 3.5 kilonewton per meter square. Okay, then ultimate design load is 4 times 1.4. It's actually is 1.4 GK plus 1.6 QK lah. This one is in British standard, we use the factor 1.4, 1.6. It's in Eurocode 1.35 GK plus 1.5 QK. Okay, so we get the design load 11.2 kilonewton per meter square. This is on the floor. Remember, this is on the floor. And the floor, the precast slab have two 4.5 meter length. 4.5 meter length. So, and if you extend a little bit, okay, 4.5. So it assumes that the length of the unit is 4.7. Clear distance is 4.5, but the length of the unit is 4.7. To calculate the bearing, to calculate the neck bearing width, but actually this is need to check lah. That's why the bearing you already learned, but I assume that now is 4.7. It's 4.7. So from 4.7 now we can calculate, apply to the reaction, because the precast, this is but here got a chamfer lah. Here got a chamfer. Suppose here got a chamfer is something like this. If you got a chamfer, is something like this. You got a chamfer. Let's say a chamfer, a chamfer here, chamfer maybe here, a chamfer here. Okay, so now the hollow core slab is sitting here. Okay, it's spanned from here to here. 4.7. I use 4.7. So you can calculate, and the load already, the design load 11.2. So half go here, half go here. So it's 4.7 divided by 2 multiplied by the load, and also we want to get the V. Now we want to get the V, and just now the width of the hollow core is what? 400 mm. Is it 400 mm wide? So From here, it multiplied by 0.4. So we get the V is 10.52 kilonewton for each 400 mm. Just for each 400 mm. Okay, if you want to use this one to design, also can, but you are going to design based on 1 meter run. Okay, you are going to design the reinforcement. After you get the reinforcement, is not how many numbers you're going to get in what, in per meter run, per the spacing, based on spacing. But if you based on this value, based on 400 mm, so the reinforcement you get based on the value you design 10.52 kilonewton, you are going to get how many numbers that you're going to distribute in 400 mm wide unit only, in 400 mm wide unit only. Okay, so now you assume a dry bearing and so on, and this is what you have learned in the bearing. Okay, dry bearing 0.4 0.4 FCU. Still remember or not? I have in the here connection here. Dry bearing. Okay, dry bearing is what? Direct bearing without bedding of or bearing plate. For dry bearing on concrete, we use the ultimate bearing stress. We use 0.4 FCU. Just now, why we limit to 0.8 FCU for the bearing plate in the what, in the corbel? Because here, the cross here, we are using steel bearing plate here. We use 0.8 FCU. Okay, so now we get this one 16, the bearing stress. Okay, the design bearing stress 16. So from here, how to get the length? Is it 400 over 2 plus 100 and so on? So this is the effective bearing length. This is the effective bearing length. Still remember effective bearing length. Effective bearing length. Already close it. Effective bearing length. Still remember here is 1/2 of the bearing length, 400. Is it? Remember, in British standard, this is called length. In Eurocode, this is called length. The width is called length. Okay, but in British standards, this is called length, which is 1/2 of the bearing length, which is half of the bearing length, just 400 over 2, is it? Because the unit of precast hollow core, divided by 2 plus 100 mm. Okay, so it means this one I get which one. So basically, this one and this one compare, is it? This will be critical. This one will be lesser lah, will be lesser. So we use this value here. How to get this value here? So we get 300 mm. So the neck, so from here, we can get what is the neck bearing width. Is it? The neck bearing width. Actually, you see, the once you get this one, the effective length, we want to get the width. The width is what? In the Eurocode is the length. Okay. In this case, actually, we just require 2.2. But in the mention in the standard, at least the bearing width here, the bearing width at least 40 mm, at least 40 mm. So in this case, we use 40 because 2.2 is too little. Is it? How to provide? Is it? So so we must actually got there is minimum we need to assume 40 mm. So from here, allowance of the sparing of the concretes and so on. So actually, this one is we want to get the bearing. We want to get the bearing. This one is all the bearing. Okay, the nominal bearing will be what plus the 20 plus 25 everything So this one actually, you go and look at it I just concern is the reinforcement here. My concern is the reinforcement. These are more on the bearing here. But from here, you get the width. Okay, you get the at the end actually is you want to get what is the length here, what is the length, what is this length to get the AV, to get the length here. Okay, to get the exactly the length, it means here we want is at the end is provide you to get this what is the length here. Okay, we got chamfer. At the end we want to get the AV lah, but want to get AV we must have this dimension first, and this dimension is depending on the bearing. Okay, it's depending on the bearing. Once you get this dimension ready, total dimension, then we can minus out the chamfer, and then okay, we can minus out, then we plus back the concrete cover plus this one, the reinforcement, the size of the reinforcement, half of it, then we get the AV. Okay, so here is why all the calculation here is to show you to get the bearing. I don't want to focus on the bearing here, huh? I want to focus on the bearing here. So you get 110. So after that, it minus up the chamfer, and then you get 95. Then the AV you plus the concrete cover, and plus let's say the vertical reinforcement is 10 mm. For the wall here, you use so you half of it is you 5 lah. So you get AV is 120. Okay. The question is, let's say come out, actually you are not required to get all this. What you need to do is I will give you the size, okay, the dimension, give you the cover, get you the what is the size of the vertical reinforcement. You directly can get the AV lah. You can directly calculate the AV here. Okay. Once you get it already, okay. Now is to calculate the moment. Moment is what? Moment is V multiplied by the AV. AV is 0.12 or 120 mm. So you get is 3.16 kilonewton meter per meter run here. And you can calculate the effective depth. The thickness of the nib is 105 minus 20 mm is going to use 8 mm diameter, but actually it's not practical to use 8 mm lah. Okay, at least 10 mm here, is it? So never mind, you assume it's this using 8 mm, half of the main, okay, 81 mm. Okay, 81 mm. Okay, 81 mm is the effective depth. So from here, why you get the 81 mm, what you need to do? You calculate the K. Okay, class, you calculate the K is what? M divided by BD square FCU. You calculate the Z. You calculate the AS. Okay, calculate the AS. The right, something like this. Okay, something like this. So at the end, I just want to show you is basically something like this only. At the end, you get the AS. You get the AS. Okay, you get the AS. So you're going to use 8 diameter, 8 mm diameter with a spacing of 250 center to center lah. Okay. You can go and calculate for it lah. Okay. You can go and calculate for it. For this 137 okay, 137. Then after that convert into spacing is 250 lah roughly. So then after this at the end is we have to check for the stress, whether so this is very thin like a slab, is it? Cantilever slab. So we are not going to provide the shear. We're not going to provide the shearing. Actually, we're not going to provide the shearing. So we have to make sure that the shear stress is less than the enhanced shear strength. Okay, the shear stress, the design shear stress is less than or equal to, okay, is okay, sorry, I think the shear stress not greater than the enhanced shear strength, the enhanced shear strength, which is enhanced shear strength here is what? Is VC multiplied by 2D over AV. Okay, so this one, how to get the VC? V, no problem, is it? Is the V divided by BD. Then the AVC is the equation, VC. Still remember the VC long equation. This one, because you got some table, once you get the 100 AS over BD in the British standard, actually you can direct to predict VC, but or you just use the equation, multiply in the long equation, you'll get C. Okay, then the VC, the allowable is the or the enhanced, the shear stress is multiplied by 2D over AV. D is 81, is it? 2D is 262. So 0.8784 is the allowable, must be greater than the actual, and to the design shear stress. So with this, we no need to provide the shear link. If you're in the if you're using Eurocode, this one check, there has a check also, is it? There is the equation to check the shear without shear reinforcement. Okay, but the concept also the same. You can multiply with 2D over AV. So at the end, this is the detailing. This is the detailing. Okay, chamfer is 15, and we are going to have a U shape. U shape here. So every this one, how far? We got 8 mm here. We are going to have what? We are going to have every spacing of 250. Every 250, we got one. We got one. So how to do? Actually, we can provide two bar here, two horizontal bar here. Okay, two horizontal bar here, go through, actually allow it to put the hook like this. Either we want to put or don't want to put, actually it's not necessary if you can stand it. Okay, this one you see wiring bar and so on, actually not necessary to provide what actually exactly what you need is this one okay, only this one. Okay, so I think we have covered it, and we have actually, suppose I got planned to teach another connection. Actually, there are many type of connection, which is a half joint. Half joint, you see how I am not very sure. If let's say I did not, next week, if did not teach you, I may just give you the notes and so on. You can go and, because in the final, I did not prepare the half joint question, the questions. I may just give you the notes and so on. I haven't prepared the notes even. But I can prepare. If got time, I can teach you If you want, I can teach you. Okay. So we have covered today about more than one already more than one, and start raining again. So here in Johor, in Batu Pahat, I think maybe I don't know the other stage how is it. But here is always this few days also always rain. Yesterday also the same thing. Okay. So we have finished the lecture for today. So I open for the Q&A if you have any question. Rain also started here since morning 8:30 until now. You have with me. Yihong. So is there any alternative beam to column connection to replace the RC corbel and knit? Yes, actually we have many. Actually we have many type of connection. It depends, but it's only it, what to say, since architect might not like the shape and appearance the corbel, we have to go to half join something like this. I mean, it's something like this. We can go to this kind of connections. Even means the connections. What Bihong asked here, actually the connection is this kind of connections. Is the connection itself is become partly of the part of the members already. We can even go is look at it here. You can see from here, you have a connection like this. So this connection actually, after we ground it everything, you can see it become a flat already. We can go this way also. So this is actually, I mentioned this is a half joint. This is a half joint that it's not almost similar, is it? Even this one we can have a, this one is extended out. Okay, this one is extended out, but actually we can actually, this is some sort of like a knits or what we can design. But the joint, I mean the beam of this precast beam, this one is called as a half joint. Okay, called as a half joint. There's a force system here. We have design, we have to take into account. If not, especially there are many type of forces here. So most likely, sometimes this one is critical. You may have a what re-entrance here. This is going to crack. One of the crack line is going to develop is here. One of the crack line is going to be no, sorry, I'm going to draw here. The other side, the other parts here. Okay, the beam, you look at the beam here. The beam here, this one sometimes want to re-entrance here. This one sometimes have a high stress, it's going to crack. So we need to provide. So it depends whether this is a shallow or deep recessed beam. We call it as a recessed beam. Okay, or we call it actually, this one is a half joint here. As a half joint here. So we got divided into two. One is depend how deep is it of this part, top part. It can be shallow, it can be deep here. Okay, shallow recess or deep recess beam. We can design. Actually, this is the one I mentioned. I suppose I plan to teach this one. Okay. Did I answer your questions? Any more questions? Yeah, that one maybe Hui Ling, maybe you mentioned that one I did not calculate exactly lah. Is 75 or what actually is important? That one I think not very important Important is you get how many numbers you provide at the parts of within 2D over 2/3 over D. Okay, 2/3 over D. Okay, important is provide at 2/3 over D lah. From 2/3 over D, we can calculate is the 2/3 over D, the dimension. Suppose just now maybe I mentioned maybe some, I want to correct it a bit. You get the 2/3 over D already. After that, you have to minus out the concrete cover from top, from the top layer, minus out of the reinforcement. So the exact dimension that you is not 2D over not 2/3 over D already. Sorry, not 2/3 over D already. So then you divide the dimension, divide into 3 bar, so you get the spacings. Okay, so exact I did not calculate It may it should be less than 104. It's suppose it's not 104, not just not directly 2/3 over D. Then you divide the dimension, that one. Okay, so I think that 175 mm, that one not a big issue That one not a big issue. You don't need to calculate, even not a big issue. Important is you get is from project provide at the top parts. Okay. Any more? Okay, for the project, for project, I think I suggest you to bearing at least bearing and the corbel. I suggest you to for between the beam to the beam and column, you design as a corbel, and then also you check for the bearing check for the bearing. You check for the bearing will do You assume because the precast and check for the bearing, because when you design for the beam ready, you are going to have the bearing ready. Okay, that's all. Bearing and the corbel will do. check for the bearing and corbel. Means officially it's just a corbel lah. The rest you no need to design lah. Between the because there too many lah. If you really want to teach, I cannot finish the column, between the column and the column to the foundation, we got the bracket connections and so on. Too many lah. But in your case, bearing and corbel will do. Okay. Then some more questions. The rest, no more questions. So if no more questions, then like this. Next week you wait for my. I will give announcement. Okay, for the precast, I will give you a free assessment of a take-home test. Take-home quiz. Sorry, take-home quiz. So today you have to submit. I don't know. Suppose you have to submit your quiz. The quiz of this pre-stress. Precast already give the quiz, is it? Or assignment? Assignment already given. This the connection using steel bracket. Okay, connection between the steel bracket last week. Okay, then I will give you another quiz, take-home quiz. I will inform you in the groups, in the WhatsApp group. I haven't prepared the questions. I will tell you maybe few hours that you need to submit. Okay. Yes, anyway, today in the attendance I already put it as combined together. Okay, combined. The attendance combined means that pre-stress and precast combined together. But no problem. For this class, I think I will just put it full full attendance. Okay, with full attendance. Don't worry about that. Okay, because they may sometimes got one or two students did not join, but got informed me because of the internet problem and so on. I will consider she or he is attending the class. Okay. Any more questions, class? So if you are happy, you learn something lah. You think you will learn something, maybe you just give a comment. 8 comment 8. 8 if you think you got learn something. So then we'll end out the class today lah. Okay. So okay, all comment 8, no question ready. So remember for next week's projects, I already give you the times. You know when to do, roughly about 2 weeks from now. During the study weeks, you need to submit. And also the I think I've already stopped the recording. Yes. Where always within this maybe tomorrow I will give you the take-home quiz possible also related to what we have learned in precast, especially in the joint, precast joint. Okay. And what else? Next week we are going to have a camera sections. So the last lectures, you all get ready get ready your camera so that we can snap a photo together for our memory. Okay. After we snap, then we can keep in the for us keep for us okay, then we can know next time we can look at it. Okay, this will be your, maybe I don't know whether it's your last lecture in your in UTHM or not. If you are taking undergraduate only in UTHM, okay, you are going to have your industrial trainings. Okay, majority of you for those who are from UTHM, direct entry UTHM. Okay, but not all maybe majority of you here is going to have your internship. Okay,